thank you for giving me the opportunity to give this talk. Okay, I think it's full screen now. So in this talk, I'll focus mostly on the description of a synthesis method of carbon nanotubes, which allows the control of the encapsulation of encapsulated nanowires. So it's an unconventional method because in chemical vapor deposition, normally people would try to achieve mostly laminar flow conditions to then grow smooth films of carbon nanotubes. But in this approach, we use, as I said, an unconventional strategy because what we do, we try to perturb the vapor rather than keep it laminar. So here is the outline of my talk. So I will briefly introduce the general feature of carbon nanotubes, departing from the hollow types. And then what I will do, I will describe the work that has been done, the general method that can be used for the fabrication of partially filled carbon nanotubes. So obviously, the method that have been mostly developed based on laminar flow. So laminar flow pyrolysis of ferrocene. And then I will focus on this new approach which we have been developing, and which is based on this local perturbation, so the introduction of local perturbation in a laminar flow. So in introducing the concept of carbon nanotubes, so we can generally depart from graphite. So considering the graphite structure, we can see that if we consider an individual layer of graphite, as we know, graphene layer, and we roll it up into a cylinder with a small diameter, what we obtain is a single wall carbon nanotube. If we have many of these cylinders which are concentrically arranged, what we could do, we could image what is the structure of a multi-wall carbon nanotube, which then is also characterized by a turbostratic arrangement of the layers. So it's more like a random orientation of the cylinders, the multi-cylinder structure. So if we want to generally describe a commonly used approach for fabrication of hollow carbon nanotubes, we would refer to the pyrolysis of a hydrocarbon. So if we consider a hydrocarbon and a carrier gas, for example, nitrogen, and we refer to an heterogeneous catalysis method, then what do we do? This type of approach could allow us a fabrication of hollow carbon nanotubes, mostly multi-wall, and so these materials can have important applications. Obviously, the most interesting features are the attractive electrical, mechanical, and chemical properties. What is particularly interesting is the chemical stability, because it allows us to rethink about the carbon nanotube as a capsule. So if we think the carbon nanotube as a capsule, then what we can do, we can think about it as a system which could protect also materials that are really sensitive to the air or environmental interactions. And we could think of encapsulating this material inside nanotubes to achieve passivation. So this is the case for metal-based nanowires, for example, iron or cobalt, nickel, which are really sensitive to especially at the nanoscale, are really sensitive to interactions with the air or with oxygen. And so when inside, the carbon nanotube can be completely passivated, so can be protected from oxidation. And this is an advantage because then we could consider this for magnetic data storage or magnetic applications, other magnetic applications. So the commonly used methods for fabrication of this type of field carbon nanostructures are mostly based on the pyrolysis of ferrocene molecule. So in this case, you can see ferrocene is a molecule which works both as catalyst source and at the same time as an hydrocarbon source. So it's both carbon and catalyst source. So what happens is that the carbon nanotube at a certain temperature of the reaction would then grow, would then obviously grow and also would be filled at the same time through a simultaneous growth mechanism. So the question is obviously how we could control the encapsulation of the nanowire, how we could avoid formation of gaps, for example, between each of the nanowires that are encapsulated. And so one of the methods that has been used in literature is one that uses chlorine as an additive. So it uses, for example, dichlorobenzene, in which chlorine radicals are used mostly to change the original stoichiometry of the ferrocene molecule. So what you have is the formation of carbon tetrachloride, which then removes carbon species from the in this case the CVD reactor, and what it does is changing the carbon to metal ratio and allowing an enhancement of the filling rates. However, obviously the problem is still that the formation of gaps between nanowires also implies different magnetic environments and sometimes also interactions between different nanowires, which then limits obviously application as well. So in this talk, I mostly focus on a different approach. So this approach, which I define as Perturbed-vapour CVD. This approach involves a different thinking of the experiment. Instead of keeping the flow completely laminar, what we do here, we deliberately perturb the flow and we introduce a local perturbation by modifying the deposition surface, the deposition substrate. So you can see in this talk I mostly present two approaches. Actually, I mostly focus on this first approach, and then I will mention a second approach, mostly for comparison. So I focus on this first approach because it's the more effective and allows the achievement of nanowires encapsulation, which is 25 times longer than the usual one that is obtained by CVD. And so by doing so, what we do, we deliberately create a hole in a standard smooth quartz surface. So with the use of what we do, we basically use a diamond cutting tool, and we deliberately create a hole in this substrate. And this allows a local destruction of the laminar flow that is otherwise present within the reactor. So as a result, what we see here is the formation of two types of morphologies. You can see a first morphology which is mostly consisting of particularly short carbon nanotubes, and a second morphology in which instead comprises of extremely long carbon nanotubes. And this second morphology mostly is found to deposit immediately after the hole that is created in the substrate. So you can see that the obtained structure here mostly consists of a flower-like morphology, or we could say a bushes-like morphology. And they grow in a quite a large area of the substrate. It's about a millimeter scale area. What is interesting here is that if we then look into the cross-sectional morphology of these structures, we can see that these structures are fully filled with nanowires. And this is obviously this result is much different with respect to that obtained with the laminar flow conditions. So you can see in this figure here, the black area here, this is the nanowire, and this is continuous along the whole capillary of the carbon nanotube. You can see here another example. So this is really continuous and fills up approximately 90% of the carbon nanotube without gaps. So this is reproducibly observed, and from the perspective of phase composition by using X-ray diffraction, we can see that, so in this case, we employ also Rietveld refinement. So by employing Rietveld refinement, what we do here, we can extract basically the relative abundance of the phases. So by extracting the relative abundance of the phases, what we see is that there is a percentage of magnetic phases, especially alpha and iron carbide. So what we attempted then is to control either one or the other by then controlling, in this case, the annealing through annealing, or by cooling. We attempted to isolate as an individual phase inside the carbon nanotubes. So by investigating through thinking about the phase transformations for the perspective of the iron-carbon phase diagram, then we annealed these nanotube structures for 13 hours. And what we observed is that there was a significant increase in the actual relative abundance of alpha iron. You can see here an increase of alpha iron and a decrease of the iron carbide percentage, and also formation of what is a partial oxidation, we could say, which is due to the long annealing times. This oxidation is observed also further after 15 hours. You can see there is a disappearance of the iron carbide in this case, and so you do have a single phase of iron, but you also have byproducts. You can see this is a transmission electron microscopy image, so you can notice the continuous nanowire, in this case alpha iron, but then in some cases you can see that there is decomposition is due to the oxidation. So we then thought about how to improve this, obviously the magnetic properties of these structures, and better control the phase composition, because we didn't want the oxide byproducts, because they also could contribute magnetically to the signals. So you can see, so in this case, I can show you in this case an example of so single crystal here. So this is an alpha iron single crystal, which is found, so you can see the preferred orientation. And this is an example of the continuous failure rates that are this is a scanner electron micrograph, which is obtained in backscatter electron mode. So it looks mostly at a Z contrast. And so you can see the very large failure rates. So as I said earlier, in order to avoid the formation of the iron oxide phase, then what we did, we rethought about the cooling step, and instead of slow cooling the sample and annealing it, what we did, we basically thought about a two-step cooling. A first step, which consisted in bringing the temperature down at the natural rate of the natural current rate of the furnace, and so this was from 990 Celsius to 950 Celsius, for example, in this case. And then after this, we applied a quench, which this means that we created a rail system. So we dynamically removed the furnace. And so the system is quenched, so a fast cooling rate is imposed. This implies that in a time scale of 10 minutes, then the whole system goes to room temperature. And so as you can see here, what we obtain is 95% of iron carbide with this approach, and we eliminate completely the iron oxide byproduct. So we further improve this by changing slightly these conditions. We cool slowly at the natural rate of the furnace this nanowires, this product, and so you can see the first step was ended at 800 Celsius, 830 Celsius, 800 Celsius, 770 Celsius in ABC. And then we applied the same quench method, the same fast cooling as a second step. So you can see that a maximum of 98% of iron carbide is obtained in BE. So when the quench is applied at 800 Celsius, when the sample is at 800 Celsius, and then the second step of cooling is applied. So this implies that there is a significant change in the stability of the iron carbide phase when you go below 800 Celsius. So if you slow cool below 800 Celsius, then I believe the iron carbide phase becomes metastable, so it decomposes faster. There is actually a process which is defined as a metal dusting process, which describes the decomposition of iron carbide. So you can see that the relative abundance dropped to 85% in C. So this implies that below 800 Celsius, the phase will be decomposing the iron carbide phase. So we then investigated the change in morphology of this structure by modifying the sublimation temperature. So by doing so, what we did, we basically changed the sublimation temperature from 140 Celsius to 500 Celsius. And so you can see that there is a significant change in the morphology that is observed here. You can see that these open-like structures are then found to modify into closed one. And there is another modification. You can see, as in this case, the green arrow, and here also with the yellow and with the red arrows, you can notice here there is a significant shift of the reaction towards production of micrometer scale particles. So this implies that the reaction, when you increase the sublimation temperature too much, then the reaction shifts towards another environment, towards another regime, and so implies that this byproduct, these large particles, imply that there is probably an homogeneous nucleation process that is due to the sudden increase of concentration of carbon iron species. So we then continued to investigate the cross-sectional morphology of these structures. So you can see here, so the average dimension of this flower-like structure is about 10 micron per each, and so you can see the cross-sectional morphology still shows long filling rate. So in this structure, the carbon nanotubes are still fully filled along the wall capillary. And this is really astonishing, because it's really different than what happens with laminar flows, because when there are laminar flows, then only partial filling occurs. And you can see that what we found is also a connection between this filled carbon nanotubes and the large micrometer scale particles. So you can see here there is a continuously filled carbon nanotube indicated by a red arrow, and here there is with this magenta arrow, you can see the high metal content of the large particle. So you can see that there is somehow an open growth, looks like an open growth mechanism, since these two things are connected. So it looks like that there could be catalyst migration also from these large particles. So in C, you can see also this example of a continuous filling. This is an STM image. So this is mostly showing you with different contrast the heavy components, the atomic number contrast here. And so as a comparison, as I mentioned earlier, so we also try to investigate a different type of local perturbation. So instead of creating a hole on the deposition substrate, we deliberately created a rough surface with the same type of diamond wheel tool, so you can see that what we basically created is a boundary layer between a laminar flow and a rough surface. So what happened was that then you can see here a different morphology is obtained In this case, we obtain a radial morphology. So this, you can see the carbon nanotubes were found to grow radially out from a core. What is quite interesting is this is observed in all the substrate. So it's really large-scale production, is in large amounts. What is interesting is that when investigating the cross-sectional morphology, again we see extremely long filling rates. You can see here is an example of an individual nanowire, different micrographs. You can see here, also here I give another example of a single crystal. You can see this is a nanocarbide single crystal, and the continuity of the nanowire is really clear. And what is also interesting to notice that there is it appears to be a rotation at the end of at the closure points of the nanotube. It appears to be a possible rotation of the nanowire, because there is, you can see there is a difference, a different lattice spacing that is observed when measured, when investigated by selective higher electron diffraction. So there could be also a possible rotation of this nanowire. This is obviously requires more investigation. And so this, in conclusion, perturbed-vapour, so locally perturbed-vapour CVD is a method that allows growth of really continuous nanowires. These nanowires can be chosen to be either alpha iron, iron carbide. Obviously, when you control the cooling rate, then you can easily obtain iron carbide nanowires by applying fast cooling, by applying quench method. So you can reach a phase control. In the flower-like structures, what is very important is that the nanowires are 25 times longer than what achievable in a laminar flow approach. So you could think about this for fabricating devices. What we are thinking is to investigate the magnetotransport properties now of these individual nanotubes, and to see whether there are interactions between the magnetic moments at the interface between the graphitic layers and the actual nanowire. And so the continuity of the nanowire is the most important feature of this method. And so we believe also that the oxidation effect that is observed in the case of the flower-like structure can be controlled if instead of argon we use argon nitrogen. So we use a reducing environment, and we control the flow rate of the argon flow, then the oxidation effect can be minimized. And here are the acknowledgments of my talk and the funding, and thank you for the attention. Thank you.
Thank you, Doctor. Thank you. Thank you so much for your presentation.
Thank you.
So anyone have any comments or questions, you can please ask to Dr. Filippo.
Yeah, just a short question if it's possible.
Sure.
Yeah, I would like to know what is the main or the critical parameter to control the nanowire diameter, please?
The diameter. Okay,
yeah,
so the diameter. Okay, so actually, so in the case of this second morphology here that I show here, if I come back to the slide, you can see the core of these structures here. So we found that actually the core of this structure is comprises of particles, which are we believe they are firstly produced. So there is a first a formation in the first step of some kind of onion-like structure, and then somehow the reaction shifts towards nanotube growth. I mean, we believe that to scale up the dimension of the nanotube, we need to scale up the dimension of the particles that are at the core here. So there is not an individual particle here, but rather there are many particles. So as you said, the particle size fixes then the actual outer diameter, I believe, of the nanotube. But I think the initial nucleation fixes the particle, whereas the possible presence of an open growth doesn't change the nanotube diameter anymore, but rather, so if there are two feeding methods, let's say, so if the nanotube is, if the particles are encapsulated also from an open tip, then what is surprising is that the actual diameter is quite uniform, I have to say. You can see here, this diameter here is quite uniform.
Uniform, yeah.
And so in some cases, I can show you here, if I show you the previous method, oh yeah, here, you can see here, so we found catalyst particles directly connected to the tubes. There is a clear connection. We don't know if there is a multiple stages approach, but it seems that it seems that there is the catalyst particle can fix the size of this nanotubes, the diameter. But in this case, it looks like the particle that may be originating this structure may be large at first, and then there is a certain step which then drives the nucleation. But the mechanism, we believe the mechanism is complex because it needs to justify the full filling, because it's 25 times larger than a standard nanotube growth. We could say super growth. So we believe that possibly the mechanism is complex. But it seems that, for example, it could be that at first there is a nanotube nucleation and then it shifts towards an open growth. You can see here this connection of the catalyst seems to point out that there is somehow an open growth that is happening. But the initial stage, the really initial stage, is a complex. It probably needs. It will need more investigation, I think, to understand what is the actual transition. If there is multiple steps, if there are multiple steps involved, what is the at which stage it goes into from a closed growth to from a tip growth, for example, to a open growth. So this is a complex one.
Okay, thank you.
But it seems many stages are involved, I think.